right, so now what we'd like to talk about is the test statistic for the difference in two independent sample means, and come up with the test statistic and how to compute the test statistic along with what we call the degrees of freedom. And as you probably have noticed, that formula for the degrees of freedom is quite a doozy. So we talked about in our previous video that about x bar 1 minus x bar 2. So x bar 1 minus x bar 2. So the idea, what we have to come up with now is the distribution. So if you'll recall in previous discussion, we talked about the distribution of x bar, and we found out that this was normal with a mean of mu and a standard deviation of sigma divided by root n. So that's the distribution of x bar. So now the question is what is the difference between two x bars? So again, let's just start off with the assumption that the first population here follows a normal distribution with some mean and some standard deviation, and we're going to go out and collect a sample of size n1, and that population 2 is also normal with its mean mu2 and its standard deviation sigma 2, and then we'll go out and we'll draw a sample of size n2. So again, under these assumptions and the fact that we know sigma 1 and sigma 2, then the question becomes, what is the distribution for x bar 1 and x bar 2? So the first bullet point here, we have the difference of two normal random variables, and it is beyond the scope of this course to go into the gory details, but the fact of the matter is x bar 1 minus x bar 2 under the normality assumption is normally distributed. And just like we had to come up with the center of the distribution, here we have the fact that the center of the difference of two independent random variables x bar is then equal to the mu1 minus mu2. Hopefully that kind of makes sense. The weird part is here with the standard deviation of the difference of two normal random variables. It is not the difference of the standard deviations, but it ends up being this thing right here. So here we now can formally state that the distribution of x bar 1 minus x bar 2 then is distributed normal with a mean of mu1 minus mu2 and a standard deviation of the square root of sigma 1 squared over n1 plus sigma 2 squared over n2. So now we have the distribution properties of the difference of two sample means. So now we're ready to go take a look at the test statistic. So let's just note that the test statistic, in this case under the normality assumption, is the z test statistic. And the test statistics are always, and you'll probably notice from the single means, it's information involving a sample minus information based on the null divided by the standard error of information based on the sample. So in this case, we have x bar 1 minus x bar 2 minus mu1 minus mu2 under the null hypothesis divided by the standard deviation of x bar 1 minus x bar 2, which we know from up here is this guy right here. So we just divide by that big ugly looking thing. Right? So we know that mu1 minus mu2 under the null hypothesis is always going to equal, and by our previous video, 0. So this term, for the most part, is always going to equal to 0. So our z test statistic then falls down to x bar 1 minus x bar 2 divided by sigma 1 squared divided by n1 plus sigma 2 squared divided by n2. But we don't know sigma 1 in practice, and we don't know the population standard deviation of the second population. So as we discussed prior under the single population means, when we substitute S1 and S2 for sigma 1 and sigma 2 respectively, then this changed the whole distribution property. So this now becomes a t distribution. So we have x bar 1 minus x bar 2 minus mu1 minus mu2 under the null, and now we make our substitution s1 squared over n1 plus s2 squared over n2, and again under the null hypothesis this thing goes to 0. So our test statistic reduces down to the difference of the x bars divided by the square root of s1 squared over n1 plus s2 squared over n2. Now we need to come up with the degrees of freedom. So if you don't like this capital delta, just write df. I'm fine with that. But it's this big ugly looking formula here, and luckily enough, I have written a program that will actually compute this ugly looking formula for us. So in that case, we take and we'll run a program and it'll automatically do everything for you. And notice that we'll round down to the nearest integer for our degrees of freedom. So this is everything we need. It's all boiled down to this. So to help us out, what I'd like to do is to work through this first example on computing the t-test statistic and to compute the degrees of freedom. And then if you would, I'd like for you on the next two examples, go ahead and pause the video and go ahead and give it a whirl yourself and then restart the video. That way you can practice yourself and get used to doing this once you see it done. It should be pretty easy. So let's just note that for the first one here, our t-test statistic then is equal to x bar 1, which is 12.5, minus x bar 2, which is 16.9, divided by the square root of 4.1 squared divided by n1, which is 14, plus s2 squared, which is 4.6 squared, divided by n2, which is 17. All right, so to do this, I always do a two-part computation. So if we come over here and let's just compute the numerator of this fraction. So here we get 12.5 minus 16.9. Okay, press enter. All right, so we get negative 4.4. So that's the difference in the two means. And now if we go divided by, and then we have to get this square root. So square root, so we go second square root. So notice I get a square root and an open bracket. So let's just make sure we provide another open bracket for the first term, so 4.1. So 4.1 and then squared divided by 14. And then close that bracket plus open bracket 4.6 squared divided by 17. Close. And then do one more. So one more closed bracket will get our first open bracket for the square root. So if you always do this way, you can never go wrong. So notice here, rounding to 2 or 3, I'll take this to 3 decimal places. So we get negative 2.814. All right, so now we have to compute the degrees of freedom. So our degrees of freedom, we run the program. So if you come over here to the calculator, and if you can see my spinny thing right here, you push the PRGM button, the program button, and then notice no matter what you have in here, just go on down to DF, the DF program. So there it is, program DF, and to run this program, we have to press enter again. So press enter again. So notice that this is asking for the standard deviation of the first population. So if we come over here, we can see that the standard deviation is 4.1. So we just enter that. Now it's asking for the sample size, so we just type in 14. Now it's asking for the standard deviation for the second population, 4.6. And then the sample size for the second one, we just enter 17. Press enter. So notice here we get our degrees of freedom then is 28. So that's all there is to it. So just to refresh, come back over here to compute the t-test statistic. Just write the formula out with all the numbers in it. Take the difference of the top, hit the divide key, square root. Make sure you got 2 open brackets 4.1 squared divided by 14 close, plus open bracket 4.6 squared divided by 17 close bracket, and throw another close bracket in. So I'd like for you to go ahead and pause this video and pause the video and go ahead and compute the next one. Okay, so for the next one, our t-test statistic, then it's going to be 14 minus 24 divided by the square root of S1, which is 6 squared, divided by N1, which is 10, plus S2 squared, which is 5 squared, divided by 14. Right. So coming over here to our handy dandy calculator, 14 minus 24, enter, divided by the square root. Now I'll put another open bracket, 6 squared, divided by 10, plus 5 squared. Clean that up, that's a 5. So 5 squared divided by 14, close, and then close again. So here we get negative 4.309. And then our degrees of freedom. Again, run the program. DF puts it on the screen. Now we got to start it. So S1 is 6. N1 is 10. 5 and 14. So here we get 17 for our degrees of freedom. Okay, and now we got one more. So if you will, go ahead and pause the video again and go ahead and compute the t-test statistic, and then go ahead and compute the degrees of freedom. Okay, so our t-test statistic then is going to be x bar 1, 11, minus x bar 2, which is 9, divided by the square root of, let's see, 8 squared divided by 12, plus 7 squared divided by 15. Okay. So this is equal to 11 minus 9 divided by the square root of 8 squared divided by 12 plus 7 squared divided by 15, close, close. So our test statistic is 0.682. And our degrees of freedom, well, again, we just run the program. So program DF, puts it on the screen, press enter to start it. So S1 we know is 8. N1 is 12, S2 is 7, and N2 is 15. So we get 22 degrees of freedom. Okay. All right, so feel free to rewind this, and if you need to, you can go ahead and compute these again. All right, so now this brings us to our 5-step procedure on computing a hypothesis test to compare two population means that are independent. So a little bit of hypotheses here, or assumptions. So again, we're going to formulate the mu and the alternative hypothesis. These will be in terms of differences, mu1 minus mu2. We will, step 2, compute the t-test statistic and the degrees of freedom. Step 3, we will compute the p-value. Step 4, we will make our decision, that is to reject or fail to reject, and then why. Again, we will reject the null hypothesis, when the p-value is less than the alpha level, we will fail to reject the null hypothesis when the p-value is bigger than the alpha level, and then summarize our results. And on our next video, we got some examples on how to do this.